Okay, so some example questions that we're going to go over in this video. So let's take a look. The reaction A to B has a delta G standard of 11.8 kilojoules per mole. Answer the following questions. So before I even start, I am going to go ahead and write our equation down. What was our equation? Delta G equals to delta G standard plus 5.9 log of. So we're going A to B. So we have A to B. A goes to B. B over A. Because in this case, B is the product and A is the reactant, and that would be how we would write it in. So that's our equation. And we're going to be coming back to this equation frequently as we try to solve this problem. So what is the equilibrium constant for this reaction? So we're going to go ahead and plug in 11.8 for delta G standard, right? Because here's the first bit of info that we have, this. So let's just write this down here on the corner. So we know the delta G standard equals to 11.8 kilojoules per mole. Okay, so this question A is saying, what is the equilibrium constant for K? We know at equilibrium, delta G equals 0. So we go ahead and put 0 for delta G. We know our delta G standard is 11.8 kilojoules per mole plus 5.9 log of K. Because at equilibrium, the ratio of product over reactant will just be the equilibrium constant. And we go ahead and solve for this. And this is pretty straightforward. Now, just for you guys to know, the units for this part is also kilojoules per mole. That's why they will cancel out. I don't think I specifically said that before, but this 5.9, when you multiply all those constants together, you get, and the temperature, you get kilojoules per mole. So this whole thing has a unit of kilojoules per mole also. So all that means is that we can simply rewrite this as 11.8. So I'm going to subtract 11.8 on both sides, and I get negative 11.8 equals to 5.9 log of K. I go ahead and divide by 5.9 on both sides, and what I get is negative 2 equals to log of K. And we're going to go ahead and continue on this side. Now I put both sides to the base of 10. So 10 to the minus 2 equals to 10 to the log of K. And I go ahead and, of course, this thing right here becomes just K. So now I have K equals to 10 to the minus 2. That is to be expected because the delta G standard is 11.8. So this reaction is unfavorable. And it shouldn't be a surprise that we got a K that's 10 to the minus 2. So we add that information here to the things we know, right? K equals to 10 to the minus 2. If A equals to 100 millimolarity, what does the concentration of B need to be for delta G to equal to 0 kilojoules per mole? Now what we can do is plug everything in and solve this. We can plug 0 here, put our delta G standard in, put in our concentration of A, and then solve for B, right? That is definitely what we can do. But let's go back and look at what this question is saying. If A equals to 100 millimolarity, what does B need to be at delta G equals to 0, right? So that's equilibrium, right? Delta G, when delta G equals to 0, we're at equilibrium. So the ratio of product over reactant has to equal to K, right here, right? So we're just going to set that up. We're going to say 10 to the minus 2 equals to, we don't know B, which is the product, but we know A. And we go ahead and multiply both sides by 100, and this just becomes 1 millimolarity. So 10 to the minus 2 is just 1 over 100, and you multiply by 100, and you get 1 millimolarity. Okay, so we got that done. And the next one will actually require us to use our equation. So it says If A is 100 millimolarity, what does B need to be for delta G to be negative 5.9 kilojoules per mole? So we're going to go back and we're going to use this equation right here, delta G equals to delta G standard plus 5.9 log of B over A. And we're going to plug in our delta G standard, which is 11.8 kilojoules per mole. So what we get is delta G equals to delta G standard plus 5.9 log of B over A, right? And our delta G standard is 11.8. The delta G is negative 5.9. So negative 5.9 kilojoules per mole equals to 11.8 kilojoules per mole plus 5.9 log, and we don't know B, but we know A. Now, again, remembering that this part right here is also kilojoules per mole, the kilojoules per mole simply cancel out. So that units cancel out, so we don't need to worry about that anymore. And it makes it easier for us to write everything down. So we're going to carry on, and all we're going to do is, first of all, subtract 11.8 from both sides. So we have negative 5.9 minus 11.8 equals to 5.9 log of B over 100 millimolarity, right? So negative 5.9 minus 11.8 will give us negative 17.7. So we're gonna continue this over here. So negative 17.7 equals to 5.9 log of B over 100. And actually the units are important here, so we're gonna keep it. Now I'm going to divide by 5.9 on both sides, and this will just give me negative 3 equals to log of B over 100. And I'm going to put both sides to the base of 10, so 10 to the minus 3 equals to, and what will happen, this will just become B over 100. So I'm going to multiply both sides by 100 millimolarity, and this will give me 10 to the minus 1 millimolarity equals to the concentration of B. Okay? So the next thing is, if Kf equals to 1000 per second, what is Kr? So we're just going to go back to that relationship of K equals to Kf over Kr, right? So now we know our K was, when we calculated this, let's just go back because I already forgot, 10 to the minus 2. So our K is 10 to the minus 2, so 10 to the minus 2 equals, and K forward we have 1000 per second over Kr, right? So now what we're going to do is we're going to multiply both sides by Kr. So we have, continuing here, 10 to the minus 2 Kr equals to 1000 per second. And now we're going to divide both sides by 10 to the minus 2. So Kr equals to 1000 per second divided by 10 to the minus 2. What I'm going to do is I'm going to make this 1000 and 10 to the 3 because that's what 1000 is. So Kr equals 10 to the 3. When you're dividing two numbers with the same, that are at the same base, what you can do is just minus, it'll be minus their power. So in this case it'll be 3 minus 2, and everything will be per second, and this will give me a Kr of 10 to the 5 per second. we kind of expect this. Why do we expect this? We expect the Kr to be larger than the Kf because this is an unfavorable reaction. So we would expect the Kr to be a bigger number. And to double check our work, if you just want to double check it, all you have to do is say, well, let's just do the double checking in green here. So I'm just double checking my work. K equals to Kf, and Kf is 1,000 per second. And we just said Kr is 10 to the 5 per second. And this will give me, the per seconds cancel out, and this will give me 10 to the minus 2. Right? And that's our K. So we know that we did everything correctly. At the concentration in C, what is the rate of the forward and reverse reaction? So what is the concentration in C? In C, we have A equals to 100 millimolarity. So let's write that down. A equals to 100 millimolarity. And B equals to, what do we have for B? B equals to 10 to the minus 1 millimolarity. Okay, so Kr, that's important, and Kf are important for us. So let's just make sure we have those numbers down too. Kf is 1,000 per second. So Kf is 1,000 per second. And Kr equals to 10 to the 5 per second. Okay, so just remember our reaction. Our reaction was A to B, right? So our V forward will be Kf times the concentration of reactant, which is A. Which then we plug in the numbers, we get 1,000 per second times, and the concentration of A is 100. And this will give me 1,000 times 100, so this is 10 to the 3, this is 10 to the 2, this will give me 10 to the 5 millimolarity per second. All right. The reverse would be Kr times the concentration of product. Let's just plug in our numbers in here. We have Kr equals 10 to the 5 per second. And our concentration of B is 10 to the minus 1 millimolarity. And this will give me 10 to the 4 millimolarity per second. Now, kind of how to double check this is that if I go back to C, what was my, at a delta G that is negative 5.9 kilojoules per mole, the forward reaction is favored. So let's go take a look. Well, our VF is at 10 to the 5 millimolarities per second, and our VR is at 10 to the 4 millimolarities per second, which means that the forward reaction is moving at a faster rate than the reverse reaction. So everything is holding true, and we're good to go. Now, the next one, an enzyme increases the Kf of the reaction to 10 to the 7 per second. Okay, so this is telling you that the Kf, not the rate of the forward reaction, the Kf is being increased to 10 to the 7 per second. It's not saying it's increasing them by 10 to the 7, it's saying it has been increased to 10 to the 7. That means my Kf cat equals to 10 to the 7 per second. Now, what we want to know is, what is Kr cat? On the surface, you can literally spend way too much time doing a bunch of things. One thing that you can do that will really make this simple is that we know that K has to equal to Kf cat over Kr cat, right? So I am just going to go ahead and use that. So what was our equilibrium constant? I think it was 10 to the minus 2. I just want to make sure. Yep, 10 to the minus 2. So 10 to the minus 2 equals to 10 to the 7 per second divided by kr cat, right? And going over here, and I go ahead and multiply both sides by kr cat, and I get and then I divide by 10 to the minus 2 on both sides, so I get 10 to the 7 per second over 10 to the minus 2 per second. And what I'll get is kr cat equals to 10 to the 9 per second. And this works out because if I plug in 10 to the minus 9 right here, I get 10 to the minus 2, which is my equilibrium constant, right? Now, the other way to do this is to say that, okay, well, kf has been increased to 10 to the 7, right? So what was our original kf? So let me I'm going to write the alternate way to answer it in green. So let's look at what our original kf was, and we're going to have to move up because I don't remember it. Kf was 1,000 per second. Okay, 1,000 per second. So let's write that down. Kf, 1,000 per second is 10 to the 3. So I'm just going to write 10 to the 3. And kf cat is 10 to the 7. So obviously kf cat is nothing but kf times 10 to the 4 because it's been increased to 10 to the 7. So all I have to do is multiply kr, my original kr, which was, let me remember, I can't remember what it was. I have it right here, we're going to use it. 10 to the 5 per second. So 10 to the 5 per second times 10 to the 4, which will give me 10 to the 9 per second. So there's a couple of ways to do this. I mean, there's also more complicated ways, I guess. You can come up with a more complicated way to attack this problem. But I would say these are the two easiest ones. Just depends on what you're comfortable with. But you can always check your answers by dividing kf by kr and making sure you get the equilibrium constant. Can an enzyme turn an unfavorable reaction into a favorable one? And that is a big no. Why? Why is this a big no? Just let's look at our reaction progress diagram right here real quick. And energy. A to B is an unfavorable reaction. Just to make sure, I don't remember again. I'm old. My memory's going. Alright, so here we go. Delta G standard is 11.8. Okay. 11.8. So we have A here, B here, for example. This is just using the example that we had above. So, and we're going to have our reaction go through a transition state, right? And let me erase this. And what will an enzyme do? All an enzyme will do is lower the transition state. So here's my new pathway. The delta G, or delta, if these are under standard conditions, the delta G standard has not been affected in any way, because the delta G standard is simply the difference between the levels of A and B, and that has not changed, right? Just the energy of activation has changed. So that's a big no to that question. What does it mean when we say an enzyme's activity in a cell is at 50%? Does it mean that an enzyme has a half of its potential catalytic activity? So this is actually very important because it not only affects enzymes, but it affects other things that we'll be talking about later. An enzyme, you can think of it as being either off or on, a binary switch, where it's either active or inactive. So binary switch, right? Now, if you can be either at 100% activity, so this is 100%, and 0% here, how can you get 50% enzymatic activity? Well, a single molecule of an enzyme is either at 100% or 0%, but there's not a single molecule of that enzyme in the cell. There's many copies of that enzyme. So when we say 50% activity, let's write that down. 50% activity. We mean that 50%, and let me just draw this here. We mean that 50% are active and 50% are inactive, right? When we say, for example, 25% activity, we mean that you have 25% active and 75% inactive, and so on. So even though the enzyme, a single molecule of an enzyme, is a binary switch because you have a population of them, when we were talking about 50%, 25%, 10%, 80% enzymatic activity, we mean that a portion of them are completely off while the other portion is completely on, and that's how you can modulate enzyme activity within the cell. Again, this is more important than what happens with a single molecule because the subject that we're studying is cell biology, not the biochemistry of a single enzyme molecule. I will talk to you guys later. Bye-bye.